Well, I've already recorded this video once, but it did not have any audio. Now it's got audio. Okay, so here's an electric field problem. It's kind of tricky though, so we're going to kind of work through it, but it's not insane. So imagine for a second that I've got a negative charge right here. Let's just call it negative 25 microcoulombs, so times 10 to the minus 6. Let's say I have a positive charge right here. It's positive 50 microcoulombs, so times 10 to the minus 6. Let's just say they're separated by a distance of 0.12 meters. First question I've got for you is if I divide these into quadrants, quadrant 1, quadrant 2, and quadrant 3. Of these three quadrants, which, if any, could there be an electric field equal to 0? Another way of saying that is if I put in a positive test charge into these different regions, where on the axis, always on the axis for this, where would this charge never feel a force? And I say that because remember, a force is equal to a charge, that's like the test charge you could put in there, or some other charge, times an electric field. So if the electric field is 0, the force is 0, where is that? So pause this video for a second, think about that, take a guess, 1, 2, or 3, or 1 and 2, or 1 and 3, or 2 or 3, or none of the above. And see, we'll see in a second what that is. So, you've paused the video, right? You're thinking about this? Who knows? Okay, so let's actually work this out. If we put a positive test charge somewhere in region 2, let's just drop it here. If we do this, it is going to be pushed to the left from the 50 microcoulomb charge, and it's going to be pulled to the left by the negative charge here. Both forces are going to the left. They will never cancel each other out. In fact, if we were to draw electric fields here, this would be similar to what we drew earlier. This is like a dipole, two opposite charges. And all the electric fields would be going to the left. So it is not the middle. If you guessed 2, whoops. Let's take a look at the right side, region 3. Now region 3 gets a little weird. If I drop a positive test charge over here, it's going to be pushed away by the positive charge here. But it's going to be pulled to the left by the negative 25. So maybe you're thinking, ta-da, I did it. It's section 3. But it's not. It's not that. Here's why. If we think about electric fields, remember, are equal to K, Coulomb's constant, times the charge creating the field over R squared. And we've got two electric fields here, the one generated from the 50 and the one generated from the negative 25. For the 50, not only does it have a large numerator because it has a larger Q value, larger charge, but it has a smaller R squared value because it's physically closer. If we look at the other electric field to the 25 microcoulombs, it has a smaller numerator and a larger denominator because it's physically farther away. It's got to go all the way over here for that R squared value. So it's not that. Okay, so we are never going to actually see a 0 over here because the 50 microcoulomb electric field, the red one, is always going to be bigger than the blue one. So we're never going to get a 0 on this side, which leaves us with, well, either the answer is 1 or the answer is none. So let's think about it. We go over here, we say, boom, what do we got? Well, the positive is going to push it away this way. The negative is going to pull it this way. So they are opposite directions. Could they ever be equal? Well, if we kind of work out the same logic from before, the red has a larger numerator, but it also has a larger denominator. So we're going to be large up top, but also large in the denominator, which is going to make things smaller. Whereas for the blue, we do have a smaller numerator, but we also have a much smaller denominator. So maybe there is some location in here where everything balances out and they happen to become equal. Even though this numerator is smaller for the blue, maybe I can decrease my distance enough that at some point they've equaled and matched out, especially because that's an R squared value. So somewhere over here in some location on this, flat x-axis here, there's a point P that is at a perfect distance away such that these electric fields are equal. We'll call this distance x for right now, okay? So the real question becomes now, how far away from that negative 25 microcoulomb charge do we have to be in order to generate an electric field of 0? Because remember, this one from the red, we can call this that way, and the one from the blue is going this way. So we got to pick positive and negative directions. Let's just call this one positive, this one negative. It doesn't really matter. What will matter in the end is that the net electric field will equal 0. And this means that the electric field from the 50, which we're calling positive, plus the negative electric field from the 25 equals 0. And that makes sense because a positive plus a negative is 0. And what we can really say here is that the electric field from the 25 is just going to equal the electric field from the 50. Okay, so that's really what we're saying right here. How can we set this up? Well, let's just set it up mathematically and see what we get. If we do this for the 25, we know we're using this equation, kq over r squared. We've got k. Our charge here is the negative 25 microcoulombs. We're going to ignore the negative though. Remember, we drew that negative in the picture, that E field's pushing to or pulling to the right, and this electric field is acting to the left. We've already designated positive and negatives, and technically by setting up this equation, we've moved the negatives around and worked it out. So let's just not worry about it. So the 25 microcoulombs would pop in there for Q, and then divided by, well, r squared. In our case, r is this value of x. So let's just dump that in the denominator, x squared. This has to be equal to the electric field generated by the right charge. So K times that Q, which is 50 microcoulombs times 10 to the minus 6, divided by, and then what's our r squared value down here? Well, it's not x squared. We need to go x, and we need to go this extra 0.12. So in the denominator here, it's going to be x plus 0.12 to the squared. Okay. Now, a kind of nice little thing that you may or may not know about is because these are similar equations and both of these have microcoulombs in it, we could actually dump these microcoulombs out. Like if you were to divide each equation by 1 times 10 to the minus 6, it would dump that. And if you did the same on this side, it would dump it. So we don't really care about what type of microcoulomb or coulomb or megacoulomb these are. It dumps out either way, as long as they're the same. Okay. The other thing that dumps out here is Coulomb's constant, the 9 times 10 to the 9th. I don't care about K, it's on both sides of it. It's going to divide out. Which means that whenever we're here solving this, the only thing we need to think about now is cross multiplying, which is kind of a pain in the butt. If you're looking at this and you're like, Mr. Botzer, there's a way around that. You don't have to cross multiply. Yeah, I see it. We'll talk about it in a second. But if we did cross multiply this, we're going to have 25, because I dumped the units there. And then you're going to have, well, x plus 0.12 squared. So I'm going to square this out. So I'm going to expand this, and I'm going to get x squared plus 0.24x plus 0.12 to the square. And then that's going to equal 50x squared. Now what I'd be able to do is I can distribute this 25 all throughout. And then now I'm going to have like terms in terms of the x squared quantities and the x squared quantities on the other side. So if I do this, what I'm going to have is the 25x squared, 25 times 2.24, 25 point, whatever that is right there. But then I'm going to subtract 50x squared to the other side. So I'm going to get negative 25x squared. That's because I had 25x squared minus 50, so I got negative 25. And then distributing the 25 throughout is going to give me plus no, it's not going to be 0.6. It's going to be 6. Whoops. Eraser, eraser. It's going to be 6, right? Am I doing that right? Let's double check that. I just want to double check that real quick. Yeah, it gave me 6. Good. And then plus, and at the end here, we're actually going to get 0.36. And that's going to equal 0. Now, if you're looking at this, you're like, how do I solve that? Whoops, I forgot something. What is it? It's the letter x. If you're trying to solve this, I wouldn't want to factor that because that's going to look a mess. But what you can do is just say this is a coefficient A, this 6 is a coefficient B, and the 0.36 is coefficient C. A, B, C. And at that, you've got a quadratic equation. You could do negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And that will give you the value of x. Remember, when you do the quadratic, you're going to get two answers here. One of the answers is going to be non-physical. It's going to give us some like negative number more than likely, which means if it gave us a negative number, it's implying that, because negatives is to the kind of the right, it's implying that it's over here, which we know it's not over there. We know it has to be in region 1. So when we do this, we actually just find that x is going to equal 0.29 meters, okay? Which is very helpful. If you didn't want to run that quadratic and you were looking at what we had initially here, well, you're right. We don't technically have to, but it's bad math practices to do a little trick. If I wanted to, I could just take the square root of everything, which if I did that, I'd have like the square root of 25, which is 5, over the square root of x squared, which is x, and this would equal, well, whatever the square root of 50 is, divided by x plus 0.12, okay? This is much easier to play with because I don't have to worry about this piece right here. I don't have as much distributing. I don't have a quadratic in the end. I can just solve this for x. I still have to do a little bit of cross multiplication here, but it's not bad, and I can directly solve this for x. Interestingly enough, you will still get the 0.29 meters. The reason why we don't do this is because what could be the case here, if you're a mathematician, is what would happen if x equaled 0? Well, now I've got 0 in a denominator here, and that's a huge issue, and I can't even take this, I can't even put it there to begin with, but I can't take the square root of that anyways. If x equals something like negative 0.12, I've just blown up this right side denominator because now it's 0. So because we don't know what x is, it's kind of bad practice to take a square root of it. If x over here, look at this as well, this is a negative number for x. That means, you know, you can kind of do some weird things mathematically and kind of put yourself into a hole you don't want to. You don't want to do that, okay? So it will still work out. As physicists, we ignore all that stuff that the mathematicians go crazy about. But if you wanted to be most proper, you could do this just with the quadratic and call it a day, okay? It's not really that crazy of a problem though. The big things to understand is why this is region 1 for the position of x instead of region 2 or 3. And then when we set this up, just setting them equal to each other. If you can set this up right here, you did it. You know the physics. The rest of this is just a tricky math problem with quadratic, but with time, we can get it. This type of question doesn't pop up often, but it is something that we have seen in the past, and I wanted to make sure that you've seen it at least once, so you're not blindsided by it in the future, okay? But with that, this is finished, and it's got audio this time. Adios.